use them. So a lot of vocabulary, a lot of understanding what things are called and where they go in the process. So our first question is confidence intervals and hypothesis testing are two major categories of statistical inference. That just means we use statistics to prove something is true, or at least to try and prove that it's true. Now, on the basis of what you've heard already, are null and alternate hypothesis statements about a population? Are they statements about the sample, or are they statements about them both? So which one of those three is it? When you're talking about the null and alternate hypothesis, what are they talking about? The population or the sample? Any ideas? Population or the sample? Okay, here goes. Maybe you were too shy to tell me. They are about the population. The null hypothesis says that the population value P is this number. And the alternate hypothesis says, nope, it's not that number. It's bigger than that number. It's less than that number, or it's just not the same as that number. But they're all about the population value. And we're trying to test whether the population has changed in some way. So null and alternate hypothesis are always statements about what's happening to the population. Here's this next one. A previous example hypothesized that the proportion of babies born during a full moon is 1/29.53. You're probably wondering what that 29.53 is. It's how many full moons there are in a year, roughly, because we're not exactly 52 weeks and so on. So the question was here, hypothesis that proportion of babies born during a full moon is that fraction. Let's call it 1/29, right? Okay. The hypothesis of interest is that, as if, right, but I've just repeated that. What is the population of interest? There we go. Specify the population parameter of interest. Well, that's the proportion of babies born during the 24-hour period. It's that one. Now you want to write this down as a null hypothesis. And I've got a little thing over here. I don't know why we don't have a not equals here. It wouldn't have been that hard for them to do it, but evidently they don't have one. So if you ever need to do not equals to, you type in exclamation mark equals. Okay, so the null hypothesis is that P is equal to 1/29. What's the decimal to go with that? 53. And that's all you're doing. Right now, we're doing really quite small steps. We're not doing the whole process. We're not even doing parts of some of the questions are just bits of a process. They're just the first part, not even the second part. Now, professional tennis players like Martina Navratilova, John McEnroe, Jimmy Connors, okay, there's some of them quite old, but you might have heard of them, are all left-handed. And define the parameter P as a proportion of professional tennis players, current or retired, we don't care, who are left-handed. Researchers are interested in the hypothesis that it is greater than 10%. And the reason why they're interested in that is that in the general population, about 10% of us are left-handed. So in this class right now, there's probably 2 left-handed people. Do a side addition. Put the little, do you know the little reaction symbol? Put your thumbs up if you are left-handed. I made a prediction it's 2. going to stop the sharing for a second, that way I can see all of you. Right, so you're going to, I'm not left-handed, but oh, good. Haley is left-handed. Anyone else? Okay, I said 2, it was 1. I'm not that far away, right? It's not 18. There is very good evidence that if your dominant hand is left-handed, that there's very good evidence that there are certain attributes that are also associated with that. I've heard, I don't know if I believe it or not, that left-handed people are more musically inclined, or at least artistically inclined. So I'm going to have to pick on poor Haley because she's the only left-handed one we've got. Haley, do you play an instrument, or are you kind of into art? I know she was able to communicate with me because it looks like she's using an iPhone. You can always type in your answer, Haley, if you're not able to audio. And she has, so let's see what she said. Well, Haley's not artistic. There are a number of sports where being left-handed or left-footed is actually a big advantage. Does anybody know of any sport where left-handed people are actually sought after? Because there's not many of them. Left-handed or left-footed?
It's nice in baseball, but not anything too special.
Okay. It's nice because left-handed batters are used to being the ball thrown by right-handed throwers, right? And so it's easier for them to play that way. Right-handed throwers aren't used to playing with left-handed batters so much. I guess that's the advantage. Would that be reasonable?
It's more against the pitcher than,
Right, gotcha. Well, there are 2 sports that come to my mind. One similar to the baseball, left-handed boxers called southpaw, if you're interested, are actually tend to do quite well in the sport. And in a game you call soccer, but I call football, anybody who's left-footed is quite rare. So they like people who go, because you have a left wing and a right wing and so on. You like people whose dominant foot is to be left-footed when they play on the left side of the field. It's not good if you're right-footed. A lot of people are really good, right, and they're ambidextrous, right? They kick equally well with both feet. And that's a really good talent if you've got it. But there's 2 examples. So there I go and drift, but it's almost called drift. Left-handed people then in tennis. So what is the population of interest here? Well, they give us a list and we're just interested in those people. I'm not sure. Are you looking at the screen now? I've kind of lost my group. You are? So you're saying question 3. That's essentially what I want to know. I'm just going to move my window over here so I can see you. It's always helpful. So what's the population of interest here? Well, we are looking at, I believe it's that one. The population of interest is all current and retired professional tennis players who are left-handed. Would you agree in this story that's what they're looking at? Now you want to write that hypothesis in words, being careful to specify the population and the parameter of interest. So which one are we looking at? So researchers are interested in the hypothesis that proportion of people in the world who are left-handed is greater than 0.10. And can you see it there? You can't see that? You're shaking your head.
Are we supposed to see a website or something?
Yes.
No, we don't see it.
Okay. Then that would be something. Well, that's what I get for opening and closing all these different windows. Now I'm going to have to go back Do a screen share, do a basic, click on it. Can you see it now? Question 3.
Yes.
Yay. Okay, we're just my usual mucking about with Windows. So tennis players, population interest is this hypothesis test. They're interested in the proportion of people in the world who are left-handed is greater than 0.1. That's what you're trying to prove evidence of. Right. Question 4. We have to state the null and alternate for each of the following potential research questions. So you're always, in a hypothesis test, you're always hoping to be able to prove something, right? HA, right? You want to prove whatever the HA says. The null hypothesis is nothing's changed. P equals a number. And the alternate would be P is bigger than that, it's less than that, or it's just not equal to it. So here is what we're interested in. Will increasing of the speed limits in interstate highways lead to an increase in fatalities? So I'm going to look through the nulls and see which one. Well, this one says increase the speed limits on this highway increases fatality rate. That one says it doesn't. So I know it's not that one. So it might be that one. Changing speed limit will result in a change. Well, they want to, here's the key here. You see that phrase there, increase. So it's not the third dot. And this one says no change. It's not that one. This one says will not result, and that's that one. So after all that hard work, I get this one. Now, when you set up a null and alternate hypothesis, you get what's called a one-sided. Actually, they should say left, right, but they're clumping them together and calling them one-sided tests, or you get two-sided. A two-sided hypothesis test always comes about when the alternate is it's different from the null, right? It's just not equal to it. In this case, it's one-sided because of that, because we're trying to prove it's increased. Okay, this one, when a coin is spun on its edge, what's the probability that it will land heads up is equal to 0.4? Or is the probability, that's a key word there, is the probability 0.5? Okay, so I'm looking at that and I'm saying, well, what are you trying to prove? You're trying to prove it's not equal to 5. So I'm going to go through the alternates and see which one says it's not the same as 5. And the probability less than 0.5. Probability is not 0.5. There we go. It's that one. And that's a two-sided because it could be bigger or less. Okay, here is a statement, question 5, and we are going to write down what the null, what the alternate would be, and what type of test it is. Nationwide, it's estimated that approximately 29% of adults smoke. And then they go on and then say, suppose we believe that this is now different. Okay. The null hypothesis is always going to be equal. So if you've only got one with an equal sign in it, pick it. Because the null hypothesis is it's whatever the number used to be, 29%, and it's still that number. The alternate is based on this part. What do you want to prove? Well, we want to prove that it's different. So which one of those dots, 1, 2, 3, or 4, would be the alternate, that it's different from 0.29? Isn't different just another way of saying it's not the same as, right? It's not equal to. So, you know, there are different ways of saying it, even although they mean the same thing. And since this is a not equals to, can't we pick that one? It's two-sided. If a different world, if we thought it had decreased, then would it become a one-sided? I wish they gave you the option of left and right-sided, but one-sided is what it is. A new drug to help battle anxiety has been developed that claims that only 18% of patients have shown some kind of side effect. Okay. Drug side effects. An independent lab plans to test this new drug, and they believe that it's more than that. See the more part? So between what they told me at the start and what I'm trying to prove, which it's more than 18%, I should be able to set it up. Well, you're going to have a dead easy time with these questions. That's always equal. Remember what I said? Null hypothesis is always equal to, in this case, 18%. And we think it's more. So the alternate is, we think the percentage is bigger than that. So are we getting a little bit more comfortable how you can take a story and turn it into a null and its corresponding alternate hypothesis? Now let's look at the next one. A botanist for a large rose farm, I guess there must be such things, told the management team that 23% of the roses suffer from some insect damage, which pretty much means you can't sell them. I mean, you could give them to, potpourri company or something, right? Based on current sales, data management team thinks that the proportion of roses damaged by insect might be worse than that. Okay. There is the null. It's 23%. That's what, the botanist says. Company that's, or the factory, whatever you want to call it, has got the roses. They think it's worse. Is that going to be a one-sided or a two-sided test?
Is it one-sided?
Yeah. We think it's worse. Isn't that one direction? If they said they think it's different from that, or it's not the same as that, or other phrases like that, then you would have chosen the two-sided. Now, the alternate here is that they think it's worse. So when you look at it, that one, if I can put a dot on it, there we go. Is it that the P, the percentage of insect damaged roses, is bigger than 23%? So the null is equals, and the alternate is either bigger than, less than, or not equal to. That's your choices. Well, here's a new story. Suppose the present success rate in the treatment of a particular psychiatric disorder for the relevant population is known to be 0.71, right? So it's 71% effective. A research group hopes to demonstrate that the success rate of a new treatment will be better than that. So P is going to represent the success rate, right? If you look at this, then P equals, and it's going to be 71%. That's what it is right now. And we think, or they think, they can do better than that. And there's your null and alternate. Next story. Suppose a statistics teacher asks his students to each randomly pick a digit 0, 3, 5, and 7. His general, right, so you can only pick one of those numbers. His general theory is that the proportion who pick the number 0 will be less than what you would expect in a random situation. Now, since you're only giving them 4 numbers to pick, would you agree that P is 1 out of 4? And I'm just going to turn it into a decimal, which is that. The null hypothesis then is going to be P equals nothing 0.25. So far, so good. Now, what's the alternate based on what he has said here or she has said?
It will be less than.
And it's almost a direct translation from English into mathematical symbol. Isn't that P less than 0.25? Right, the more of these guys you do you get into the the language of how you set them up. This is just the set up hypothesis part, right? We aren't doing anything else after that right now, just setting it up. And of course, you have to get that right if you want to do the rest. I'm just curious, since I've got you all here. You can only pick 0, 3, 5, or 7. Clear your mind for a minute. 0, 3, 5, or 7. Okay, pick one.
5.
Oh, well, thank you for telling me. Right, here goes. How many said 0? Wow. That's pretty strong evidence that the guy's probably right then, isn't it? Nobody even picked 0, at least. That's what it seems like. Right, let's move on. Question 10. Suppose that a woman thinks that she might be pregnant, so she takes a pregnancy test. Consider this situation to be like a hypothesis test. Write each of the following words. The null hypothesis. Now, remember, the null hypothesis generally states that nothing's going on, right? So which of those two would be the English phrase for what the null hypothesis would look like?
Not pregnant.
Right, nothing going on here, she's not pregnant. The alternate then, would you agree, is woman is pregnant. The conclusion, if there is enough evidence to reject the null hypothesis. Basically, you get the little test and the little blue thing and the arrow, whatever it is that you're using, and tells you, would that be the pregnancy test shows that she is pregnant? Oh, if there's not enough evidence to reject the null hypothesis, then that just is that one. I should have phrased that. The conclusion is, if there's not enough evidence to reject the null hypothesis, doesn't that transfer as the pregnancy test does not show that she's pregnant? All tests, including pregnancy tests, are not 100% effective, right? They're like 99.99% effective, but there is a 1 in 10,000 chance that it gets it wrong. And if you do the other one, then it's that one. This one here, you'll just read through it and I'll let you figure it out. And this one, we can move on. In the last census, it was determined that 8% of school-aged children in a certain state live with their grandparents. So the census collects evidently a fair amount of information. 8% of school-aged children in a certain state live with their grandparents. Now, there are lots of reasons why that could happen. The parents may be dead. Maybe it's a single mother and she can't cope with looking after her children, so she's given them to her grandparents to look after. Whatever it might be, 8% of children are in that situation. Okay. Suppose that there's going to be a bill to support a tax break for seniors, right? Because if you're looking after some kid, it costs money, right? You have to feed them and clothe them and who knows what else. And this congressional member plans to take a random sample of school-aged children to see if that percentage, and there right at the end is the key. Aren't we trying to prove that it's now bigger than it used to be, right? The last census, 8%. He thinks it's more than that. So one of these 5 null and alternate hypotheses is going to be the one that we're going to do. So I'm going to go through and only focus on the alternates for a second. So this one, the percentage of school children in the state who live it remains at 8. Ain't that one. Is less than 8, not that one. Remains at 8%, not that one. And is greater than 8%. Do you see how we got that one? The null hypothesis is the percentage of school-aged children who live with their grandparents remains at 8%. And the percentage of school-aged children who live in their grandparents is greater than 8%. I wouldn't have put the or less in, but who knows why they did that. That would end up being, it's 8% is the null hypothesis, right? Nothing has changed. And now he thinks it's greater. So that's what it would look like, right? 8% live with the grandparents. He thinks it's, why did I hit that button when I said greater? There we go. Oh, they're next to in the keyboard. They just hit the wrong key. Explain what the population is in this situation. Who are we counting in this story? All school-aged children in that state? All school-aged children living in the state who do not live with a grandparent? All school-aged children in that state who live with one or more grandparents? All people who have ever lived in that state? All school children who have ever lived in that state? Which one of them is the population? Where are you getting that 8% from? 5 dots. Which one are we getting it from? There's a sentence there that kind of tells me the answer. Okay. Which one of these sentences here is the population, the people you're getting your data from? That one.
3 or oh,
Oh, I'll check in case I'm wrong. All school who are living in the state who live with one or more of their grandparents. The population is that. That thing there is the sample, right? Now, the population of interest then is the proportion of school-aged children who live with one or more of their grandparents. So it's that one. So that's the population. The proportion comes from the sample. And this one here is very similar, so I'll let you go through that one yourself. Now we're back to left-handed people. About 10% of the human population is left-handed. In this class, it's about 5%. Suppose that a researcher speculates that artists are more likely to be left-handed. Sally Whitehall. The researcher surveyed 450, I'm assuming famous artists, and finds that only 63 of them are left-handed. Okay. Define the parameter of interest. Well, P is the proportion of the general population of artists. No, the parameter is all artists. The parameter P is a proportion of that. Is that one? Aren't we interested in only artists here? So the population is artists. And what do we want to count? We want to count if they're left-handed. Now, the null value that they're talking about here is, you know, when you do here, nothing has changed, right? It's 10%, that's what the population is like. This number here is called the null value. It's also called in textbooks P with a little baby knot next to it, right? P with a little knot. It's called the null value. So in this case, it's that. The null hypothesis is that one, and we believe they're more likely. So we are thinking that the percentage of adults, artists, I should say, who are left-handed is greater than 10%. Now, it then says what proportion of our sample are left-handed? Well, 63 out of 450. I'm going to turn that into a decimal. 63 divided by 450. And that ends up being, right, would you agree that is bigger than 10%? So there is some evidence that it might be true. But that could just be luck, right? Randomness. To calculate a p-value for the hypothesis test, what probability should the researcher calculate? The p-value is the probability that the sample proportion would be. I hate these weird phrasing. At most as large, at least as large. Doesn't that just sound weird? Right. So we are looking at, we think it's the p-value. Can you remember Friday when we calculated a p-value? Isn't the probability that the z-score is greater than or less than the number, right? That guy. Now, in this case, the p-value is the probability the sample proportion would be. Oh, I'm trying. Oh, of course, there's numbers in this thing. Right. Let me get it here. I got it in front of me. Just checking my answer because I've got it written down somewhere. At least as large as 0.14 for a sample size of 450. If the population actually is 0.10. This one is pure memory. Which one of these 5 dots is the z-score? It might not use the same phrasing that we did, but it's one of those. Isn't that the only one where you take some and subtract the other? That's it. What is the appropriate value for the numerator? Oh, the numerator is the standard error. So I'm going to have to leave this for a second and remind you. Okay, where's my... I've lost it. There we go. Right. Just remind you what these calculations for the standard error are. Standard error is the square root of P naught, 1 take away P naught over N. P naught is the guy they call the null value. In this case, it's 0.1. You notice it's not the 14 from the sample, it's the guy from the null hypothesis, right? That's the guy that we use. So in this calculation, it's going to be the square root of 0.1 times 0.9 divided by 450. So here it goes. Square root of 0.1 times 0.9 divided by 450. And the answer that I got here is 0.014, I guess, 3 decimal places. Are you okay with the calculation of how to find the standard error? Right. This is going to be the standard error for all hypothesis tests that have a single proportion. P naught, 1 minus P naught over N. Okay, before we go back to the homework then, let's talk a little bit about it's called significance level. We use the letter alpha, it's called the significance level. It's essentially the percentage times you are going to state the alternate. I might call this hypothesis is true. I'll abbreviate that when it isn't. So basically, alpha is what percentage of the time are you willing to be wrong in a hypothesis test? And you calculate the p-value. And we've done that on Friday and we will definitely do it again. But right now, you just assume that you know it. And you test it against alpha. So if your p-value is like 0.03 and your alpha is 0.05, then you are able to say that HA is true. If your p-value is greater than 0.05, I guess we'll give that guy the equals, then you are only allowed to say not enough evidence. Hopefully you remember that from Friday. So in these questions, somebody's going to give you a significance level, an alpha. They are going to give you a p-value, and they are going to say to you, what conclusion can you come to if that was the numbers that you had? So now let's return back to the homework and see what that looks like. Right, are you looking at question 14 and 15, guys? You can nod your head or shake your head. Are we doing it? We're thumbs up. Thanks, Jessica. Right, here we go. I have an alpha of 0.01 and a p-value of 0.002. Would you agree that the p-value is less than significance? Right? 0.002 is smaller than 0.01, right? Then you can reject the null hypothesis. The p-value is less than the significance level. So when we say that HA is true, the alternate is true, another way of phrasing the same thing is to say that you reject the null hypothesis. In fact, if you read a lot of textbooks, they have a big long sentence that says, there is enough evidence to reject the null hypothesis, and so the alternate hypothesis is true. So you can either say the first bit of the sentence and imply the second, or you can say, as I prefer, the second bit is true. Now, suppose the p-value is 0.42 and the significance level is 5. So the p-value is 42%. That's much bigger than the significance level. There is not enough evidence in that story. If the p-value was 0.04 and the significance level is that, so this time it's less, then there is none. So isn't the check basically find the p-value? If it's less than alpha, you've got evidence to prove what you're trying to prove. If it's bigger, there's not enough evidence. Now, given the convention of declaring that a result is statistically significant if the p-value is less than 0.05, what decisions would be made in this situation? Okay, start with the first one. If you have a p-value 0.36, which of the two do you choose? P-value is 0.36, right? And your significance level is 0.05 for every question. So what do you do with the first one?
Isn't it
Nope.
rejecting it?
Say again?
Isn't it rejecting it?
Okay. Don't want to move beyond this until I'm comfortable that we've got the idea. So what I'm going to do then is return back to the whiteboard. Show how it's going to work. Right. So here is your test. If your p-value is less than alpha, then you can reject the null hypothesis. Rejecting the null hypothesis is the same thing as saying the alternate is true. Right? You just got to remember that there's more ways to say the thing. Right? Now, if your p-value is greater than alpha, then you're going to have not enough evidence to reject the null hypothesis. And instead of writing all that English to reject the null hypothesis, you could replace it by to reject H naught. And that would be just a shorthand way of saying the same thing. So suppose the significance level is that number, right? In question 1, we do the whole work and we get a p-value and it's 0.09. In the next one, we get p-value and it's 0.03. Third one, we get p-value and it's 0.007. And the last one, we get a p-value and it's nothing 0.43. And that entire sentence, I'm going to call it A, so I don't have to keep writing it. And this entire sentence, I'm going to call that B, so I don't have to keep writing it. Okay. Significance level is this number. The p-value is that guy. What conclusion, A or B?
B.
Agreed? Isn't the p-value, right, greater than alpha? Right, what about this one? A or B now?
A.
Are we a bit more comfortable now about the choice decision? Right, look, for completeness, let's finish this then. P-value of 0.007, A or B? What do you do?
A.
Isn't 007 smaller than 0.5? You got to remember the decimal places make a difference. What about this one? What would you do if the p-value was 0.43 then?
It's B.
Are we good? Right, so let's return back to those questions and maybe we can get them out the way a lot quicker now. So the first usual question, can you see question 16? Right, okay. In this story, alpha is 0.5, right, 0.05. If the p-value is 0.36, top one or bottom one, which do you do?
Bottom.
0.004, top or bottom this time?
Top.
Right, yep. Somebody was doing that, know what you meant. And 0.03.
Top.
Right? Isn't that less than 0.05? Right? So all we're doing in that question is somebody told us the alpha and the p-value, and we have to say, okay, what's the final conclusion that you come to? Do you reject the null hypothesis or you cannot reject? At least that's the way they're phrasing this one. Oh God, this is the last question. Okay, here goes. Consider this quote. In a recent survey, 68 out of 100 consumers reported that they preferred plastic bags instead of paper bags. If there is no difference in the proportion who prefer each, the chance of such an extreme result happening by randomness is about 0.0003. Because 0.003 is less than significance level, they didn't say it, but I know that's what it is, 0.05, we can conclude that there is a statistically significant difference in people's preferences. Now we're going to take all that story and fill in these boxes. Now the p-value is which one of the numbers mentioned here. They didn't call it a p-value, but we should be able to figure out which number, which decimal is the p-value.
It's 0.0003, isn't it?
Yes. Now the level of significance, I've already said that one, isn't that the 0.05? Sample proportion.
60.
What would be the...
Oh,
Agreed. I was going to say p hat. Is that guy right? 60 out of 100. The sample size, hopefully that one's kind of trivial, right? So when you read a story, oh, I forgot, didn't realize there was an E. There is a null value here. That's well hidden. Right, the null value is H, right? H naught is P equals something. Now they phrased it something like this. There is no difference in what you like, paper or plastic. That's what the null would be. There's no difference. What would the p-value be in that world?
it would be the same as A, wouldn't it?
No. What would p naught? That's a better phrase. What would the null value be? P naught. So we would write down P equals. Yeah, there's a problem here. There are two guys in the world called P. One is P value, which is this guy. Now maybe when I take over the world, I'll call it Q value or something, right? But right now, that's the P value. This thing here is, what percentage should it be if there was no difference? People like paper and plastic the same. What would you get there? It's a decimal. What would it be? Phrase it this way. If I said half of you like plastic and half of you like paper, that's what they're saying.
So 0.68.
0.5. The 6.8 that you're giving is the sample. But if there wasn't, that's just what my one sample did, right? 6 out of 100. But if nobody cared, right? If the big picture was it made no difference, it would be 0.5. Our sample is different from that because we've managed to show that there's evidence. Whew. Okay, bye-bye for now. Remember